Welcome to Ames Lab, AI Mission for Scientific Knowledge. Today we explore the application development frameworks. Software architecture is the basic structure of a program. Think of it like the blueprint for a house. This blueprint shows all the main parts. It details how these parts connect and work together. Architects decide on this structure very early. This plan guides the entire building process. A good plan makes the software strong and flexible. Without a clear plan, things can become very messy. It's the skeleton that holds the software body. Initially, most software was built as one large unit. This is called a monolithic architecture. Imagine a single large building containing everything. All offices, all departments are under one roof. Every function of the software is tightly packed. The user interface, business logic, and data access are combined. If you needed to change one small part, you touched the whole. This was simple to understand at first. It was the most straightforward way to build applications. Consider an online store as an example. In a monolithic design, everything is one big program. The product catalog is part of it. The shopping cart is also inside. Customer accounts are managed there too. Order processing happens in the same large system. All these components are tightly interwoven. If the product catalog feature needs an update, the entire store might need to be redeployed. This made updates slow and sometimes risky. This monolithic approach had its reasons to exist. Early applications were often less complex. Development tools were simpler back then. Deploying one single application was easier. Teams were often smaller and worked closely. The challenges of distributed systems were not yet common. So, building everything in one place made sense. It was a direct way to get software running. This method served well for many years, but as applications grew, new challenges appeared. As software became more complex, issues arose. Monolithic systems started to show their limits. A small change in one part could affect others. This created a risk of breaking the entire application. Testing became a huge task. You had to test the whole system for every minor update. Scaling the application also presented a big problem. If one feature needed more power, you had to scale everything. This was often inefficient and costly. Imagine that online store again, now very popular. During a big sale, the payment processing part gets busy. In a monolith, you must boost power for the whole store. This includes the product browsing and user reviews, even if those parts are not under heavy load. This is like renting a bigger building for one busy office. It's not the most efficient use of resources. Technology choices were also very rigid. Once a programming language was chosen, it was hard to change. Then came the idea of microservices. This is a newer way to design software. Instead of one large unit, it uses many small ones. Each small unit is called a microservice. Each microservice handles one specific job. For our online store, one service might handle products. Another service could manage the shopping cart. A separate service would deal with payments. These services are independent of each other. These small services talk to each other. They usually communicate over a network. This is very different from a monolith. In a monolith, components talk directly inside one program. Microservices allow for greater flexibility. Different teams can work on different services. They can even use different programming languages. This approach breaks down complexity into smaller pieces. It's like having specialized departments in separate, smaller offices. Each can operate and update on its own schedule. Microservices offer several important advantages. One key benefit is better scalability. You can scale only the services that need it. If the payment service is busy, only that gets more resources. This is much more efficient than scaling a monolith. Resilience is another major plus. If one microservice fails, it doesn't always crash the whole app. Other services can often continue to function. This makes the overall system more robust and reliable. Development teams can also work more independently. A small team can own one or a few microservices. They can develop, deploy, and scale their service. This autonomy can lead to faster development cycles. It also allows teams to choose the best technology for their specific service. One team might use Java, another Python for different tasks. This technological diversity can be a powerful asset. Updating software becomes less risky and faster. You can update one small service at a time. However, microservices are not without challenges. Managing many small services can be complex. You need good tools for deployment and monitoring. Communication between services can add latency. Network issues can also cause problems. Testing can be more complicated. You need to test how services interact with each other. This requires a different approach than testing a monolith. Overall, there's more operational overhead initially. Two major trends have fueled the rise of microservices. The first is containers, like Docker. Containers package an application and its dependencies together. This makes it easy to run services consistently anywhere. It simplifies deploying many small services. The second trend is cloud computing. Cloud platforms like AWS, Azure, and Google Cloud are ideal. They provide tools to manage and scale microservices easily. They offer services for databases, messaging, and monitoring. These technologies make microservices more practical. The journey of software architecture continues to evolve. We are seeing even more refined approaches. Serverless computing is one such trend. This allows developers to run code without managing servers at all. It fits very well with the microservice idea. Each function can be a tiny, independent unit. Service mesh technology is also gaining traction. It helps manage the complex communication between microservices. It provides features like security, monitoring, and traffic control. Artificial intelligence is starting to play a role too. AI can help optimize microservice deployments. It can predict performance issues. It might even assist in designing better architectures. Imagine AI tools suggesting how to break down a monolith, or automatically scaling services based on real-time demand. The goal is always to build better, more reliable software that can adapt quickly to new needs. This ongoing evolution is exciting for developers and users. The future of software architecture looks dynamic. There is no single perfect solution for every problem. Monoliths might still be good for small projects. Microservices offer power for larger, complex systems. The key is choosing the right tool for the job. Understanding these different approaches is valuable. It helps us appreciate the technology we use daily, from simple apps to global online platforms. Everything relies on these underlying structures. The world of technology changes rapidly. New ideas and tools appear all the time. Staying curious is the best way to keep up. Learning about software architecture can be fascinating. It opens a window into how our digital world is built. This video is brought to you by Ames Lab, AI Mission for Scientific Knowledge. Please subscribe to Ames Lab and follow the trend.